No, we're not. I'm gonna say it's not gonna be a live stream. Then I'll start. I'm gonna take video of myself. It'll become very apparent why I will be doing that. Test. So, knot theory works better if, when you start learning it, you have a piece of string. So everybody take their piece of string and make sure it looks like this. So knot theory is about having closed loops in R3, which means in 3 dimensions, you treat your knot theory like this. So it's always a closed loop. It's not like the knots on your shoes. Your shoes are open when we have this. But the thing that we can know about this is that if we deform it in any way, if it goes like this, we can still do this back. This is called the unknot. It's sort of like the zero for knot theory. Remember that it's always closed. So we can but now, if we go back to this way, I can knot it. And what knot do we have here? Still deform it like so. You can sort of see that when I did that and I let go of it, sort of get a knot now. Can't keeping this part the same, we can still deform the structure and it's still knotted. Now, this is like the basics of knot theory. It really doesn't require any higher math or algebra, but those play in, but you can learn like the basics that way. So if there's a 0, there's probably a 1. I think what I did right now when I knotted it, we had a trefoil. So that's like the 1 of knot theory. Now, knot theory has these moves. They're called Reidemeister moves. If you take a knot and close it, and you do these moves on it like this, this is type 1. So there's this concept called ambient isotopy, but it's easier to understand planar isotopy. That's sort of a big concept. It has more meaning, but it's very intuitive what we want. Like I said, with the deformations that we did, it was still the unknot. That's ambient isotopy. We can ensure that these Reidemeister moves also preserve that. So let's do type 1. It should look like this. So to do this piece. Yeah, okay. We do type 2, where we have 2 strings, like so you just do this. That, so go that, back. So you go, these can go both ways, like the loop can go loop to that, and this to that. And the hard one is type 3. You do a cross. So I want to do this. Do a cross. Then I move. We can like do a cross where you like move it back and forth. Yeah, it's sort of so first you have the over crossing and under crossing, and then you have a loop that is above, or no, on top of it. And then we move that through here and back. Like start with this here. Wait, yeah, it's just doing that. It's sort of hard to see. So yeah, those are the 3 moves. So what we can so that's the basics. And now we can go to like applications. So he was interested in the DNA thing.
So is this applicable to like data? Like, is it like, I mean,
It's
like,
not data science, it's totally just science.
it's digital.
It's not data science, it's just science.
Oh, okay.
Yeah. Although some people are using deep learning to understand a hard problem. It's called the unknotting problem. So remember I said like this is equivalent to ambient isotopy. Now he had a problem. You guys are able to do the unknot really fast. He took time. So like hypothetically, let's say you have your iPod or your obviously people have experienced this. Take a rope of any kind or a charging cable, whatever, put it down, comes back knotted. You know it's the unknot, but it takes you time to unknot it.
Right.
And you'd think that that's easy to undo, and humans do it all the time. To specify a computer to do that is actually very, very complex. It's like an unsolved problem in mathematics. There are large heuristics that can solve it in the general case, but recognition of the unknot is hard to do. It's not intuitive that it's hard to do. And I'll go pull up that page in Wikipedia. So let's go a little step back. First, we want to understand this. Let's do the P complexity time. The P complexity, there's a theorem called P equals NP, where polynomial time versus non-polynomial. So basically what it's saying is you have a set of easy problems and you have a set of hard problems. The hard problems are in NP and the easy problems are in P. It's much, it's sort of easier, think of it like this. So every algorithm in O notation, which means that you have either n to a power or lower, is called the P complexity class. So it's O(n) of x approximately, while the NP class is O of 2 to the power. But what we want to know, but what's unsolved is that whether you can recognize the unknot in P, which means that you don't need an exponential amount of time or space, you just need a polynomial time. And that's just basically like, essentially, is it efficiently solvable? So yeah, I mean, it's a lot more theoretical, that concept. It has to do with Turing machines. And let's just go into a little bit about Turing machine or something. So a Turing machine is like a model of computation, but what we do, there are two ways like a Turing machine can operate. Like we can do the formal definition, but like the idea is with NP time, well, it's not non-polynomial, it's non-deterministic polynomial. So a deterministic Turing machine will right to left and just do the steps. All modern computers pretty much do operations in P. Technically, they can do operations in probabilistic P, but that's way beyond our discussion. Now, what if you had a mythical computer? It has been referred to like an oracle machine or whatever, where instead of what you could almost like guess the solution or get to the solution like immediately. So it has, instead of being deterministic, it's like non-deterministic. You can like execute a bunch of items and get to the answer real fast. It's like shortcutting everything. But those have, the 2 to the x thing. So that means like to get there, you have to evaluate 2 to the x states. Like an oracle, would like just tell you to shortcut everything. So yeah. So I think we have a little bit of the theoretical background. Now we can sort of try to play with them through the computer. Anybody have any questions or? Try to make this bigger. We're going to use a tool called SnapPy. It's freely available.
just download Snappy on your laptop?
Yeah, it's for Mac, Linux, and Windows. Um, so we're going to be looking at this knot. This is so this is another knot, figure 8. This is 4 crossings, so remember the trefoil that I made had 3 crossings. This has 4 crossings, and so we can do this. So like this is a knot that we'll be looking at on the computer first. This snappy kernel is sort of hard to read, but so anyways, so when we do manifold 4-1 is a shorthand in knot theory. It's reference a table. So the first thing that was done in the 1800s when knot theory was created was to make a table of knots. And we can look at that directly. So yeah, I mean, you have like the 0, this is like the 1, the 2, 3, and they're numbered in a way. It tells you this has 3 crossings, and it's the first prime knot. 4 crossings, and it's the first 4 crossing knot, and 5, and so on. An important thing about knot theory is you count by the number of crossings. So we have 3 crossings there, 4 crossings there, 5, 6, 7. You can see that this table is not even binary. It's not like it doesn't grow like a binary encoding or anything because of part of like the ambient isotopy thing. So like we could have. So this is the 800, 8. The 4-1 is the knot that we're looking at using this program called SnapPy. And their tutorial basically is this is all the code you would need to make a knot that is like that, and then study it in SnapPy. Like we have the crossing. See, we create 4 objects. 4 variables here. Crossing for x and ABDC. So for x in that, it calls the crossing on x, and then assigns that back to the variables. Then these 3 lines tell you what's the crossings. It encodes the crossings, and that creates the link object. Anybody have any questions about like this syntax? Like this is just a This is just a list comprehension. for x in the string, not theory string, creates a crossing object. Assigns that. And these are the crossing operations. And then we do something called a link. So in knots, we have sets of concepts that are related to knot theory, but not necessarily knots. A link allows you to have more than one. You have more than one loop. Like you could have like two pieces of string, or so forth. But what this command does is it looks at the figure 8 knot, which is pre-programmed into this. So this is like looks up in the table called manifold. It looks up the figure 8 knot, and then it executes the method is isometric to it, and then it returns true. And there's links, there's tangles, but let's look at a link first, because we haven't looked at that. So the Borromini rings, think of like, so remember we said before that they're a single piece of string. Well, this is an example of a link, or the basic link, where there's there are 3 crossings: over, under, yellow, over, under, red, red, under, yellow, blue, over, red. But these are separate strings. So instead of having only one string, you can have n strings. But when we constructed the link before, and then we said is isometric to, what Snappy did was it understood the link was actually a manifold for 1 when we knotted it all. When we created that link object, then it figured out using this method that it's equivalent to that. So what? Yeah, so I think it has to do with the triangulation. Not exactly sure about that. I think it's probably part of the manifold. So so a hyperbolic thing is where it's basically the difference between a map and a plant, like we call those earth things. The difference between like a map and a sphere that has a map on it. So like in regular trigonometry, you have a triangle where everything's like, adds up to 180 degrees. Now, if the triangle, if we say that they can be hyperbolic, that means they can exceed 180. They don't, so like they're on a sphere, so they embed it on a sphere. Like remember that in an original definition of a knot theory, you have a path in R3 of a string. Now it looks like what it computes here, hyperbolic gluing equations. So remember we had a link, and when they called volume, it probably took all the pieces we had, and when it glued them together, and then it outputs the volume when it decomposes is like a manifold and stuff. I'm not sort of doing a bad explanation of this, but yeah. So like SnapPy has concepts of like triangulations, where like it's not just a continuous manifold; it can have other things like that. Yeah, I think probably should take like a break now, or if any has any questions.
So, how, I guess I'm trying to figure out, how is this used in topology? I haven't mentioned that yet.
No, this is topology.
Oh, this is at the, okay.
So, there's topology, which is the study of, sets and open sets, but generally they also study like manifolds that like donuts. Like difference, like an old joke is, why can't the topologists know the difference between a donut and a coffee cup? And then they say the joke is they have the same genius, which actually means topology is the study of Play-Doh. Everybody use Play-Doh, like, or understands, or silly putty. So if I took a donut and put Play-Doh on and make it out of Play-Doh, it'd be really hard for you to eat it. So it probably wouldn't taste very good. But what I could also do is I could take the Play-Doh, I could make sure, and I could make it look like a coffee cup and work like a coffee cup. Assume my Play-Doh is, allows for liquid. And what you do, what the idea is that you just take the donut and then you deform it without creating an extra hole. So that's what they mean by genius. Now, it's a closed, as long as it has a hole. It's not like, because like, the donut hole, like when you make a donut, you actually, and they have a donut hole, you can actually think of that as you have a flat manifold, you deform it into something that almost looks like a donut, and then you remove the sphere. And I think that works, that works the same way. You cut it out, you cut it, it also has to do with open and closed sets. I mainly did this, when I studied this in school, I did this not from like an analysis or set theory sort of way. It was more like a combinatorial way. And also sparing you all the calculus, other stuff. So the idea is that you have genius and then you have holes. But knot theory just basically restrict, it's a subset or of topology, or topology works with deformations. We also have the concept of deformations. Like this string, it could be your string. I could make it really big or really small, whatever, it doesn't matter. But I could take the trefoil or even the unknot. When I said remember the unknot is like a donut. And all I did was deform it. Now, knot theory just adds the crossings idea. Well, you have, remember the first three things we did, we added the loop thing. They add those features and the concept of ambient isotopic, meaning we have the table, and that table is a table of prime knots, meaning that you can't form them any other way. I mean, they are closed under the Rademeister moves. Like, you could do all the Rademeister moves you want, you'll still be one of these. Like the unknot, we could deform that into a coffee cup. The trefoil, I don't know what you deform that to. You could make it a bagel that looks like a trefoil, and actually there's a way to do it. It's funny. You can make a bagel that, if you cut it in a way, it will be two loops. Where, like, have you guys seen like a Mobius strip, and you cut it one way and you have two? We can do it with the bagels too, but when you do that cut, you are you are deforming the surface. You're not following the Play-Doh rules. Well, you're not following the rule that I must have a hole. You are introducing a hole, or you're changing the topology of it in general. So. So he asked a question about molecular knots. And that there was an article we went through where, like, the DNA has binding sites. So. But I didn't really study that part a lot. I studied more about topological quantum computing, a little bit in school, and then so the biggest part of that is this type of particle called an anion. And it's a quasi-particle, but it means that it really sort of exists. It's like, electrons exist, anions can exist in very obscure quantum fields. This also ruins your experience about any Marvel movie when they have, like, quantum physics. Once you understand the level of quantum physics, the Marvel movies just get annoying. You just tune out the whole thing. None of it makes sense. It's like they said, like the Mobius strip, and like, okay, like, you're not defining a closed time like curve. You're just saying Mobius strip, and then like Iron Man just does it in like 5 seconds. Like, well, you didn't really do anything. You're not. Well, I don't get about Iron Man, whatever. Like, he has the arc reactor and stuff, and like, one. He could corner the market on energy, or even with vibranium, like when like the original source, Wakanda. So, like, you have all this vibranium that apparently can not only be used to arc reactors, but as a limitless source of energy. And you guys, like, I don't understand why, like, if you have these limitless sources of energy, you could do anything. They use it in a way that is counterintuitive and also weird. Iron Man could have just cornered the energy industry, and then not only cornered the energy industry, but I don't know. You have a lot of energy, right? You just give it to everybody, but like, if there's limited source of energy that you can do anything with, and it's weird. Like, in Wakanda, they have the vibranium, right? And that absorbs all the flexions and stuff. And well, yeah, I mean, they could do it that way. Or you could also make energy. You can also have limitless energy. And so, like, then the Power Stone is, like, weird. Like nobody cares about, like, this second law of thermodynamics or any other issue. It's like, you have all this energy. Where is it coming from first? And why aren't you doing other things with it? Like from my understanding with the arc reactor, he has like, basically Superman, right? So why doesn't he just create an arc reactor that does a shield around Earth? Or why does Thanos, when he does a snap, like he could do that? But if you know statistics, you could say, well, Thanos could snap and kill half of the universe, but kill also everybody on Earth. Because like there's some kind of implicit assumption that's normally distributed. So like, why didn't he do the snap where everybody on Earth is dead? And he's not violating any of these rules. Like I think it's like his fairness thing. It's really weird. Like he wanted to be fair with the snap, but it's weird. I mean, when you take a look at statistics, you could like, he never gives a rationale of like, not only like it's all random, right? But he never says that it's distributed 50-50 on every planet. So he gets rid of Earth, and then I don't know, and he has access to Time Stone, just like Doctor Strange. So why can't he go into the future, look like that would happen, go back, say screw you guys, and then like buy Earth? I mean, it's very strange. But the key part of these Annian stuff is that it's a two-dimensional system, and when you plot the path of those systems, well, when you add time to a two-dimensional system, you get a three-dimensional system, and now we're back to knots. So yeah, and the DNA thing, it's just the DNA has like binding sites where it likes itself. So the DNA, like what we saw here, it was like we had loops, and then the loops, and when you have loops, and then it like tangles and stuff, it would tangle at specific parts to preserve like some kind of structure. But yeah, so the thing about that advantage of anyons have with like quantum computing, as I'm sort of hand waving away because it's way, is that there's an error correcting system. Quantum computing, the biggest challenge for them of implementation is a thing called decoherence, or managing decoherence. That's why you have all these quantum computers are like super cold. They're like zero, like very close to Kelvin, because we go back to the second law of thermodynamics. So if I have an arc reactor like right there, and it's like outputting heat, it will decohere. I would have that's an issue. Like thermodynamically, the heat would actually can mess with the coherence of the quantum states. So like what you want is a thing called entanglement. A lot of people think that entanglement is sort of magical, and there's a lot of philosophers that make up, whatever the Back to the Future thing, or many worlds hypothesis. Number one, I mean, you can believe whatever you want. I'm not going to preach any belief of interpreting quantum physics, but if you actually really study it, it's really just a different way of statistics. You can, instead of having a distribution, like you can have a negative part of the distribution, or in quantum physics, like variables can have a complex, are not just a real number, they're just a complex number. And then when you have entanglement, that means the double slit experiment, where you have a quantum, where you can see entanglement, the wave particle duality. But when you have two quantum bits that are entangled, that means they actually just have a different way of the statistics, and you can use that to create a quantum computer which can do certain tasks faster than a regular computer, such as sorting. So a lot of people know that sorting is n log n. Well, so you can, this is, wait, I don't mean sorting. Let's do Shor's algorithm. I remember this a lot better. So this is why everybody says that quantum computing will break all encryption systems. So RSA encryption has two primes, Q and P. You multiply them together, and you have like a semi-prime number, and you can and if you could factor that number, you could efficiently solve RSA encryption. Now, what really would happen is that if we did have quantum computers that could do this, all we would do would be to create a new version of SSL, a new version of encryption, a public and private key encryption that would be post-quantum computation, which means that it would just be a protocol change. It's like just when, the Intel chips, with the exploit with the microcode, we just move it. I mean, at rest, if you had like RSA encrypted systems, and if you had access to a quantum computer, you could solve them, but the rate of which a quantum computer actually being created is so far away that it's not a real threat unless we have like a few breakthroughs in science. But as you can see, this is the runtime of it. This very, 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 very sub-exponential. It's going back to P and NP. Remember, factoring is around 2 to the x. Well, this is less. And then because of that sub-exponential time thing, you break RSA. Now, I was fortunate to go to UIC, and there you have a person called named Bernstein, which I tried to get, because he also does open source stuff like QMail, and I tried to get him to talk to our talk, like a Flourish, which was an open source conference at UIC, and I wanted him to talk because he did a lot of stuff in open source, but he's like a ghost. And as I went through the math department, got more and more friendly with people that were there. Well, not only is a ghost, he's not. He doesn't necessarily like. He sort of got involved in a class where he gave a class where he was teaching people like fast ways to do cryptography. And at that time, cryptography, fast ways, still makes people nervous in America, but at that time that's even more nervous. So then I believe they tried to block foreign people to register for that class. And I guess because UIC didn't have his back, or I'm not too sure about that, he got into a legal case And but yeah, but anyways, that's sort of an aside. He also, the only time I saw him, my brother saw him more than once because he was part of the computer security at UIC. We both had jobs at UIC doing like research programming. Like I saw him once in an elevator. He had a T-shirt that says post-quantum cryptography. There's only one person on campus that would have that T-shirt, and it had to be him, because everybody else on campus doesn't do that. Like he's I think he's like he works at UIC, or he's like he has his own website, CRPYTO. Yeah, so, and he basically uses UIC as a kind of co-location. His computer is there, co-located, sitting happily because he knows how to administrate it, and so forth. So yeah, I mean.
Does he use it for practical applications or just theoretical?
What, for post-quantum?
Yeah.
Well, once quantum computers are created, then it becomes non-theoretical. Then you'd implement it. Google's actually experimented with it, but they sort of double bag it, which is the safest way. Like, so when DES was sort of like weak, they had this thing called 3DES, which is do 3DES 3 times. Now Google is thinking, well, we could probably do those post-quantum computation things, but the problem is they're not battle tested, because if you make a new, the safest way to do encryption is always to do a library. The reason why they do that is if you roll your own, it's like sort of like a foot gun. You're probably going to shoot yourself in the foot 99% of the time because you do the encryption wrong. That's why. But when you have new encryption and new techniques, like I said, factorizing a prime number or ecliptic curve cryptography, those things are established. But the post-quantum cryptography algorithms, which have to do with other problems, are not proven. So Google double-bagged it, just like 3DS. You do the regular TLS on the outside or the inside. Well, it doesn't really matter, but like you do the post-quantum crypto algorithm on that, and then you encapsulate in regular cryptography. And they did that primarily as a testing ground to see if it could be done. Because like it would be a good test. Like once we have quantum computers, then we just implement that protocol that Google is trying to prove that works. So, but the issue is that if you use something other than RSA factoring, it's not studied as well. So there could be a shortcut. There could be like you have those. Let's pull up one. Yeah, like lattice-based. So when you choose a cryptographic system, the best way is to choose the oldest one, not the newest one. When you choose an older one, it's sort of like databases. Or like the old databases, you know how they work. You know that they work well. You know that Postgres 10, works, or Postgres, whatever, works much better than MongoDB. Because MongoDB was made earlier. And blockchain, everybody says it's sort of new. When you look at it, it's really just a database. And you notice that Bitcoin is a database and it's been battle tested and proven for a long time. But the newer coins, that are not actively scamming you, are just databases, and then those haven't been proven yet. And we saw that with Ethereum, the multiple security problems with that, and so forth. And so like this lattice-based thing, the problem is that he initiated the concept of looking at new crypto systems, but the caveat is that you still have to prove that regular computers can also not decrypt it, because you don't know if a quantum computer can shortcut it, and because if a quantum computer can shortcut it, can't shortcut it because of your design, but you don't know if a regular computer can also shortcut it either, because it's not, like I said, it's not battle tested, it's new. Like, I think RSA is from the 80s or I would say it's like from the 90s. These are like millennials or worse. So yeah. Actually, the worse than millennials. Whatever. Yeah, I'm a millennial. I don't remember. Anyways, yeah. So sort of like. Anybody have any other questions? Or?
I saw last week there was an announcement at the show that they actually, somebody did a quantum computer. Like Google, somebody announced something like that. Somebody announced.
Okay, so they announced a system that basically, so there's this term that they made up that everybody's starting to about the quantum computing field because of one issue is that, well, these are really expensive projects and we don't know if they actually can work. So they have this concept called quantum supremacy, which means that they took a problem that is totally constructed. It meets all the technical limitations that would prove that a regular computer could not do what the Google system could do. But they're still woefully underpowered compared to, an actual working quantum computer. Like we're looking at quantum computing is sort of at the beginning of the century, like 1900, like 1910, in relation to computers. So quantum computing is just starting out. And a lot of people, there's a real big imbalance because there's a lot of algorithm work and theoretical work, but the practical work is so few and really expensive. Getting stuff to 7 nanometers, just avoiding quantum effects, is only reachable by TSMC. Intel is having trouble doing that. Quantum computing, there are like five or six research groups: Microsoft, Google, D-Wave, IBM, probably a startup that is stealth or non-existent. D-Wave is sort of a startup, and Amazon even announced that they're you see a lot of software that's put around. All the cloud providers are sort of outputting their software, and there's a reason why. Nobody in their right mind would want a quantum computer on your desktop. You wouldn't even want it in a co-location. You wouldn't even want it as a server. There is no reason why anybody would want to do that, because you need refrigerant, you need networking. It would be the ultimate cloud system, because instead of, I could almost do it on laptops or like my own stuff, it's like, you can't do this because it's really, really, really expensive. It would be more expensive than the TPUs that go home as ASICs. It would be more expensive than any ASIC system, any FPGA system, any computer they could possibly make, because you need a bunch of physicists just monitoring it and make sure it actually is working. If it decoheres in your, let's say I had it on my desktop or even in Braintree, if the thing blows up and you sort of have this happened with the LHC, where they had the supercool to do the superconducting, which you also need for the quantum computer. So one of their magnets broke and flooded part of the LHC with liquid nitrogen, and that stopped them. That's what can also happen with your quantum computer. So yes, but that's just an aside, but the idea, so with topological quantum computers, they have an error correcting system which would help them avoid decoherence. There's been theoretical work that's saying if a correctly implemented topological quantum computer would have an error correction high enough that you could, it would avoid decoherence. And what I mean by decoherence is the entangled states don't like being warm. Actually, they don't like being observed or even played with. You have to do that superconducting stuff for one reason. The reason is that once it's exposed to heat, you get all these, you collapse the wave states. And it basically creates an observation of the system. Yeah, I think it's a good time for a bathroom break and probably end of the talk. So.
I got a quick question.
Yeah, that's
What if-
that's decoherence.
Yeah, so what if he just recording it? Is recording actual observers too?
What?
Does the recording act as an observer state too? Like an observer changing the state.
Yeah, that's a good point.
Back to the observer changes.
So quantum physics is observation based. An observer collapses the wave state. But observers cannot be people, they can be anything else. Like I said with the thermodynamics thing, the heat decoheres. Actually, what's happening is in the entangled state, they have no direct observer, even to the other atoms. When you introduce heat, you're collapsing the wave state and you're performing a measurement. Well, you're not performing a measurement, but a measurement effectively happens because they break their own entanglement and go to the non-entangled state. And once you do that, that's on a quantum computer, that should be done at the end of the computation. If you do it in between, it's basically like taking your hard drive and ripping it out while it's doing something.
Thank you, that was very good. Here's your screen.
The brute force, I gave 96 coordinates. And then I just had, well, here, but I still have to give it 96 coordinates. And I still have to give it 96 coordinates, so either way. That's what I'm trying to do. But I didn't figure it out, but I guess I just passed it. This worked. It works.
What? Yeah. Yeah.
I needed to put some money to you work in the same business?
Just a contract.
In what aspect?
Like education programs. No, it's pure education stuff. Yeah, things have always been years back, and education program. Hit me up. Give me some help with this and so, possible. No, I literally showed for the first one last week, so
Is it, are there free days coming up? Oh, I see why. Nobody's out here.
there's a